So, you doing good today?
Yeah.
Okay,
yeah.
good. Perfect. So it's Wednesday, right? I'm sorry, Monday, right? So it's just the start of the week. So yeah, now we're done with up to chapter 9. So we're gonna do chapter 10. So chapter 10 is about the organohalide. So we're just gonna talk about the organic compound, which is the halogen groups over here. So this is actually kind of the review actually. We have already done this in chapter 3 actually. So when we do the nomenclature for the arcane, we have bromine, chlorine over here in this case. So basically we're gonna count the carbon from where we can have a lowest possible local number for the two substituting groups. So technically, you just have to do 1, 2, 3, 4, 5, 6. Okay. So if you do this one, you can have a 2 for bromo and 4 for chloro over here, and there's the 6 carbons in the base. So it'll be just hexane. But I'm gonna put the bromo and chloro alphabetical order. So it'll be 2 bromo and 4 chloro. Okay. So that's pretty much it. If you have a 2 bromo, 2 chloro, you can also do dibromo and dichloro. But this is, what we already did. So I'm not gonna do much on this one. Just try maybe. Could you just try this one real quick, and we'll just move on. Okay, this one, because this is what we already done in chapter 3. So, but this is organohalide, so we just doing it again. But it's basically what we just did a long time ago. Okay, but just 1 minute. If you just can do it, I just move on. Okay, so this is just okay. So 1, 2, 3, 4, 5, 6, 7. So it'll be heptane, but it will be 2 bromo and 6 chloro heptane. You got it right? I mean, yeah, it's pretty straightforward. Okay, so here's the thing. The next part I want to talk about the nomenclature is the kind of a unique way to name the organohalide in 2 different ways. So we have this one over here. Obviously, you can say it's methane, because iodine. You can also say this is methyl iodide, 2 different ways. So this is actually what we already know, right? We have a carbon in the organic compound as a base. We can put your substitute groups as a prefix, cytomethane here. Sometimes you can do this way, because this is like you have a methyl group are attached to your iodine. So it's like a methyl as your substitute groups, and this is like your base. So we call this methyl iodine. So actually for this, we have 2 ways to name organohalide. That's kind of a unique one. So whenever you have this one, okay, you can actually do this one. You have 3 carbons in a base, so the propane. But there's the number 2 carbon. It has the chloro group there, so you can do 2 chloro. Oops, no space. 2 chloro propane here. But the same here, you can actually put this one as your substitute instead. So you can also do isopropyl chloride. This is also okay. So this is kind of a kind of unique because you can actually name this one. So what I can tell you is this one. We normally put our organic compound as base because this is kind of the major part of your compounds, we believe. But sometimes you feel like you have a more emphasis. It's like you think in this organic compounds, your halo group is more important for certain chemical reactions. You can put this in this way, so you can actually emphasizing there's chlorine right there. So this is how you just view the compounds, but which way to smell. So maybe you can try this one real quick. Yeah. I'll give you about 1 or 2 minutes. So you can actually have 2 names. That's possible. You can do 2 names. Okay. So obviously you can do bromocyclohexane, right? That's the first one. Okay. And you don't have to name one because it's in the cyclic compound. And then you can also do cyclohexyl bromide. It's 2 different ways. So bromocyclohexane. Okay. So you don't have to do one because it's cyclic. You can also do cyclohexyl bromide. The fourth okay. So for example, if you have this one, okay, you're definitely gonna say what 1-bromobutane, right? But you can also say butyl bromide. Makes sense, right? Yeah. So this is just kind of a unique from other nomenclature. So I think we're done with the nomenclature. So we're gonna do some chemical reaction here. The first one is we call radical halogenation. So this is actually also something we already did before when we have methane. And you can treat with the chlorine over here. You can have chloromethane, or you can say methyl chloride. This is okay. So if you have initiation of the radical reaction, because as you can see, these two are the same elements, so they're going to be homocleavage. So they become a radical chlorine over here, and this is also the carbon and hydrogen. Not so much difference in electronegativity, so they're not gonna do polar reaction, but they're gonna do also do this one. Okay. So eventually, you have other side product looks like this. Because of you're gonna have hydrogen and methyl on the radical form too. But those two combinations will make our organohalide. This is what we done before. Okay. Do you actually remember this one? Okay. So we actually did this one before. There's something we need to know additionally from this one is when we have a longer arcane. Okay. So when we have a longer arcane than this one. So whenever you have maybe butane over here, okay, and you can treat it with the chlorine again. So you have a lot of energy and some organic solvent over there. What you can do is what you can do is you're gonna have either this one or this one, these two, okay? These two. So and then let me see. So this one is about 30%. Okay, this one is about 70%. Okay. So we have two possible product we can get from this radical halogenation over here. You see there's the chloro groups on this carbon, which is more substitute with these two carbons over here. And this one is only from one carbon here. Okay? This carbon is only surrounded by one carbon here, right? So it shows the kind of a preference on where you can will do radical halogenation, either inner carbons or terminal carbons here, which you have more substitute carbons in inner position than the outside. So you have a more major products from the hydrogenated internal carbon than the other one. Okay, makes sense, right? So this is the difference between these two. Why it becomes major and the minor products over here. But the thing is the way we explain the radical halogenation is actually involved the what hydrogen will be replaced. Okay, so if you have these two inner carbons here, there are 4 hydrogens were able to replace by this one. Okay, so when they break apart as a radical form, right? They're going to have 4 hydrogens could have been just halogenated with chlorine on these 2 positions. So either you're gonna put this one here or here will be the same, right? Because they're same, right? Because they can work. So this one, and you can either put here or here will be still the same. So you can. The twos are also the same too, because you can actually rotate too. So that means in inner carbons you have 4 hydrogen and to be halogenated. In the terminal you have 6. So there will be 4 and 6. So technically you have 6 hydrogens on the terminal position, and then it's 30%. So for each hydrogen at terminal position, is even lower. So it'd be 6. So 30% of product divided by 6 is what? 5%. 5%. Because makes sense, right? Because you have a terminal position with the hydrogen can be radical halogenated. Then there are 6 hydrogens, but you have 30% of product. So for each hydrogen on the terminal carbon it will be 5%. Does it make sense? Okay. But in the inner carbon there's only 4, but you have 70% here. So 70% divided by 4 is about, I think, 17.5. Okay? So if you compare this, each hydrogen has a 17.5% chance that can be halogenated. This is only 5%. So if you look at just the product-wise, they seems not so different, but even here, it's more dramatically preferred on the inner positions when they do radical halogenation. Okay. Does it make sense? Mm-hmm. Okay. So meaning, I can give you one more. So whenever you have this, okay, and you're gonna do also this one over here, okay, and then you have this one is 35%, okay, and then you have this one is I think it's 65%. Okay, so if you look at this one here, you actually going to have this product and this product 35% and 65%. So it looks like this is a minor, this is a major product over here. But only difference is either this chlorine are going to be halogenated in this carbon, which is more substitute, and this one is only 1, 1, 1 for each terminal position here. 1, 1, 1. So that means you're going to have only one hydrogen in this position here, because there's only one hydrogen there. But in a terminal position, either you're gonna put this on here, 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 or be just all same this. Okay? So you're actually going to have what? 3 hydrogen implied in each carbon. So the 3, 3, 3. So you have a 9 hydrogen on the 3 terminal carbons over here. Okay? And there's only 1. So the chance for this hydrogen to be halogenated is literally just 35%, because there's only 1. Okay? So you have a 35% chance this hydrogen can be halogenated, replaced. But here, this is a 65%, but it's actually coming from the like a 9 hydrogen chance. So technically, this is about 7.2%. So it looks like this is a more major products, but it's simply because you had more hydrogens to be like replaced by the chlorine, which is halogenation. So technically, it was actually 35% to 7.2%. So technically, this position is more what preferred to be halogenated. Makes sense, right? Okay. So they find out they try to find out the reactivity of those. So what's happening on this radical position? So they find out that if you have the primary radical here, secondary radical, tertiary, okay. I'm sorry. Okay. Tertiary over here. If they find out the directivity, if this was 1, this was 3.5, this was 5. So meaning, if this is happening at like a certain speed, this is 3.5 times faster than this one, and this is even 5 times faster than this one. So this is a reactivity trend. So it gets faster if you go from left to the right. So this has they find out, this radical has much faster when you have more substitute with the carbon that has a radical form. So the scientists try to find out the reason why. Okay, so they try to find out so they actually try to find out the stability of the radical form. They kind of did it by measuring how much energy to make the compound as a radical form. So I can draw something. Okay. So this is a methyl, because you know hydrogen radical. So this is a methyl radical. This is the primary. This is methyl, primary, secondary, tertiary. Because it's only one R group. 2, secondary, 3. This is what we call vinylic radical. So vinylic radical means you have carbons with a double bond, and one carbon in this 2 double bond has a radical form. So it has a radical only one electron in here. We call this vinylic radical here, and this is methyl radical. primary, secondary, tertiary. This is a kind of tricky one. Okay, so you have two carbons in a double bond. Okay, and there's a neighboring carbon right next to it. So you have two carbons in the double bond, right? And there's a neighboring carbon right there, and that has a radical form. One hydrogen, one electron here. We call this a lytic radical. Because we call this position as a lytic position. So lytic position simply means that there is a carbon right next to the two carbons in the double bond. If you're pointing the carbon in that double bond as the radical form, this is what we call vinylic radical. Vinylic. Okay. So we try to measure, this is trend, and this is the trend of the stability. So if you go from the left to the right, it is more stable in the radical form. So the scientists were saying when they form the radical structure, they'll be more stable, relatively speaking. That's why they can actually react much faster in this way. Because whenever you have the radical form, but if it's not too unstable, they might have a better chance to go on the radical halogenation. Makes sense, right? Okay. So this is, they try to measure how much energy is required to detach the one hydrogen and radical, and they find that this is a lot of energy, about 460, 440, 420, 410, 400, and this is about only 370. So it's not so different, in my opinion, but still, even that small change makes some relatively speaking more stable radical form that makes the reaction much faster. So they have a better chance to be more halogenated because of that. Does it make sense? Oh, perfect. That's very good. So, all right. So then, I actually have some practical problems I can show you. Oh, yeah, let's do this together. So we have this one, okay, cyclohexane, and we're gonna treat it with the NBS. Okay. This is the N-bromo succinimide. It looks like this one. In some organic solvent like this one. And then what you're actually going to see is the bromination on the alytic position here. Okay, so this is a bit different from what we did before, right? If you do have a regular bromination, okay, it could have been just these two positions on the opposite side, right? You could remember this, right? But if you use N-bromo succinimide, meaning you're going to have a radical. You're going to have a radical initiation. And also this is kind of the mild version of bromination. So you're only going to be one bromine will be there, okay? So this will be a good example to prove that why the alytic position is very special, okay? So in this case, what you can do is here. So you're going to have a not brominated over here, but here. Okay? So either here and here, doesn't matter, it will be the same compound anyway, right? So what happened to this one is the same. They're going to break apart as like a radical, and one hydrogen radical too. Okay, and when they have a bromine comes in, there also has to be homocleavates too. So there'll be the bromo of one there and one bound to this one. So then they become HBr, and there will be only one bromine will be there. Okay, and then when they goes to here, okay, this will be replaced by this one. And then this will become this one again. Okay. So then they replace this one, And this one, the radical bromine also comes into the next second time, and they actually bond to here. So it is indeed in a radical halogenation with this MDS. This is why you're going to have a bromination on the lytic position. So we're gonna, this is what we call a lytic bromination, because you're gonna have a bromine, bromo groups on the lytic carbons. Okay. Does it make, do you want me to explain once more? No, oh, it's good? Oh, perfect. So, yeah, so this is why you had this product over here, not the bromination, this double bond is gone, something, because it's a radical halogenation. So I'll give you, so here's the thing. Here's one example I can give you. So if you have this one over here, right? And this is a lytic position, as you know. This is two carbons in a double bond, has a neighboring carbon with a radical form. So what's so special about this one is they can have a radical resonance, meaning you have a one, the pair of electrons can be also homocleavage like this, and then this can go to even there, and this can go to there. Okay, so if you do that, they can actually go interchangeably on this. So you can have a radical form here or here, and back and forth right here. So if we actually measure the electrostatic map, it's almost equal because it's also kind of symmetric on the left and right. So if it's not, it's maybe not so equally distribute the electron density charge by radical form. But if it's like a quite radical like this, like a carbon, one carbon on the side with the central carbon, they can either go back and forth. They can actually equally distribute the radical resonance electron cloud. So that makes these two lytic position carbon in radical form very stable, because it's resonant. It can resonate in a much larger area. So this is actually not going to be on the exam, but if you have a terminal alkene, okay, terminal alkene, you have a hydrogen over here. So technically, if you do the bromination here, you're gonna have either this one, these two, okay, right? Because you have a lytic position here, but it could be here too, because they can resonance, right? So there will be two products over here, but actually, you may think this might be more preferred here, but this one is actually major because it's less hinder in the terminal position. And also that's what I meant by it's not actually well symmetric, because if it's in the terminal alkene, when you do the resonance on the right and left, this is much longer. So you can do that anymore actually here. But I promise I'll not put this in the exam. It will be too difficult to, because it's a kind of exception. So anyway, I'll just move on. I just want you to know this, but you don't have to know for the exam. I don't want to confuse you or anything. Okay, so maybe you can try this one real quick. Actually, I'm gonna do this one together. Okay? Don't worry about it. But maybe you can try to. Okay. Maybe you can try this one. So just only thing you have to remember is lytic positions. Okay, and think about what might be the products. Okay? Yeah, this will take some time, so maybe 2 minutes. Okay, so does it make sense? Oh, okay, so what I just did over here is you have a lytic position here, right, obviously, but you can also do this one too. So there's a two position you can do, what, the brominated. And then the thing is they can also do resonant in here, because you have a two neighboring carbon. So you could do lytic with this two or these two. So if you do the bromination, there'll be four products over here, which is where you have what? This is kind of ortho, the two substitutes this here. But this is two meta, so they're actually the same thing. So this is actually three products there. Because you can just flip it. Like this here. So there will be three products there. Okay. Oh, okay. So I'll just stop here today.